Good afternoon, ladies and gentlemen. Welcome to the afternoon session of this meeting. It's my great pleasure to introduce Professor Stephen Blundell of the Physics Department of the University of Oxford, who will be speaking on instructive mistakes, how errors have shaped and misshaped modern physics.
Thank you, Harvey, and thank you very much, and thank you to Joe for the invitation to speak. So I believe the Oxford tradition of history, modern history at least, is that it begins after the fall of the Roman Empire. So I may have an even longer period to talk about than our first speaker, but in fact I'm going to restrict myself to really the last 150 years and call that modern physics. And actually looking back over various stories in physics, you see that really almost anything is littered by mistakes. Mistakes seem to be absolutely crucial in the way in which science advances. So I really had an embarras de richesse. I could choose almost anything. So I've selected a few, I hope, instructive examples, and I'm going to work backwards in time, starting with the most recent, and trying to maybe look at a few morals that come out from these mistakes in physics. So I guess the first one is about the case of being too willing to believe a good thing. So sometimes a wonderful result appears and it really looks like everything is revolutionized, but is it really that clear? So we're very recent, we're 2023, this is only a few years ago, and these headlines started to appear in the newspapers. A superconductivity breakthrough, maybe the biggest discovery of a lifetime. And this is going to be revolutionary. If you look a little bit more carefully, you notice that this is a result that is, it's published in the archive. So this is actually a preprint. It hasn't actually been refereed, but it's got all the journalists a buzz because this is a room temperature superconductor. If you've ever had an MRI scan, you've been inside a superconductor, and those superconductors are cooled to within a few degrees above absolute zero. If we could get this to work at room temperature, it would indeed be revolutionary, and this is what this result was showing. This material was called LK99, the superconductor of the summer, according to the New York Times. And as one scientist at Lawrence Berkeley National Laboratory, this was a theorist coming in later after the original experimental discovery, putting it into a computer, showing that this material was indeed a superconductor according to the calculations. Some of us were rather skeptical because these kind of theoretical calculations tend to be very good at post-diction. In other words, telling you that a material you found that you know is a superconductor is a superconductor. They don't tend to be quite so good with prediction. But this was a post-diction, and it all looked very good. And what was also worrying was that the scientist announced this with a Twitter or X or whatever it's called, showing the Obama mic drop, which is really showing that this is a result that is completely clear. But in fact, when the preprint came out, myself and my group, we did look at it, and it looked very dodgy. In fact, there are bits of this publication that really, I think if this had been a first-year experimental write-up from an undergraduate, it wouldn't have passed. The graphs were badly plotted. Strange thing showing, for example, the levitation of the superconductor with person's hand indicated. I don't know who else's hand that should have been, but other than a person's. So these are figures from the original publication, and what you can see they've shown is the resistance of this material drops very suddenly, just above about 100 degrees centigrade. I mean, this is incredible. This is more than the boiling point of water. This would be an extraordinary discovery if right. And there were two publications. This was a second one. Again, the data look rather low quality. They're plotting voltage against current rather than turning it into units like resistivity and current density, which is very unusual, but maybe correct. They were honest scientists, though, because one of the things they did do was a structural analysis. And one of the things they found was that there was an impurity in their material, which was copper sulfide. I'm not telling you the formula of this compound because it's not relevant. I mean, this was a total mistake. What actually happened was that this material, this impurity, copper sulfide, has a metal insulator transition just above about 100 degrees centigrade. And what they were seeing in these data was just that metal insulator transition. You can see the resistance doesn't go down to zero. And the fact that it levitates, well, graphite will levitate, will show diamagnetism. So this was one of these occasions where the journalists went crazy, but in fact there was nothing there. This whole thing was a mistake. But I don't think that's very interesting, really, just to look at mistakes that are just, in one sense, slightly incompetent mistakes. But here's another example of a similar kind of thing. This relates to a little bit about what we were hearing this morning. So this is a result 50 years ago from a Nobel Prize winner, Leon Lederman. He was to get the Nobel Prize later for other work. This is their paper in the most prestigious Journal of Physics, Physical Review Letters. And what they had done is they had looked at electron-positron collisions, and they tried to find a resonance, and probably a little hard to see their resonance here, so I'll indicate it. This is the new particle that they'd found. They called the upsilon particle after the Greek letter upsilon, and it's at 6 GeV. Now, as we heard this morning, the thing that you have to do is to really say, is this statistically significant? And in their paper, they mentioned that there was really only a 1 in 50 chance that this was a spurious result. In other words, just do random fluctuations. But if you were listening carefully this morning, you'll realize a chance of 1 in 50 is actually pretty high. In fact, this is only 2 standard deviations, and the modern standard for a discovery would be 5 standard deviations. And of course, they published this and took some more data, and the effect went away. It was just a pure random fluctuation. And so the particle got nicknamed the Oops Leon particle. Now, in fact, they did, a little bit later, they found another resonance at 9 GeV, which was statistically significant. They did call that the upsilon particle. So the upsilon particle was eventually discovered. But anyway, this was the Oops Leon particle. Okay, both of these examples, in one sense, are trivial, because these are just people being a little bit hopeless with their experimental technique, or in this case, with statistics. And I think this lesson has been powerfully learnt. So let's maybe go on to something a bit more interesting. So my own research is on a particle called the muon. I use that to study materials. And the story of how the muon was discovered is a case of mistaken identity. So let me tell you the story. So around the beginning of the 20th century, there was a revolution in physics because these new phenomena that didn't fit into the established pattern of 19th century physics were discovered. So there was the discovery of X-rays and the discovery of radioactivity, all happening at the end of the 19th century, heralding that maybe things were a little bit more complicated than people had realized. And when you had discovered, in particular, radioactivity, one of the things you had to do was measure it. As we heard this morning from the National Physical Laboratory, measurement is everything. So the way you measure radioactivity, as some of you may remember from your physics lessons at school, at least I remember the way I did it, was with this thing called the gold leaf electroscope. So some of you may have seen this. The idea is these 2 little pieces of gold leaf can be pushed apart if there's an electric charge on the top. So you charge up the top of the metal rod. The 2 gold leaves separate. But then if there's radioactivity around, that's ionizing radiation. That will cause a current to flow, and the 2 leaves will come together. So you can use this to measure the presence of radioactivity. Now, I've also sketched here the updated version of it. So they had a better version at the turn of the 20th century. They called it the electrometer. It's essentially a gold leaf electroscope, but the big difference is you've got a microscope, so you can really look through and see the 2 metallized fibers moving apart. So now we've got a way of measuring radioactivity. Now the question is, where does radioactivity come from? It's known there are certain elements that produce it, but there's also background radiation. So how could you measure that? Well, you could take this electrometer around and you could do measurements. And one of the measurements was made by a Jesuit priest in 1911, Father Theodore Wolff. And he decided to do measurements at the top of the Eiffel Tower, and he found that there was more radiation at his electroscope discharged faster at the top of the Eiffel Tower compared to the bottom. And he was a good scientist because he also did measurements in a horizontal direction. So this is nothing to do with the Eiffel Tower per se. This is something to do with altitude. Now, if there's more radiation when you go up, that tells you that maybe this is something to do with outer space. And so you could do more sophisticated measurements. So somebody who did this was Victor Hess. He did these extraordinary balloon flights without oxygen up to huge numbers of, I can't remember how many thousand meters he went up to, but it was really pretty dangerous stuff, with his electroscope, and found that this effect continued as you went to higher and higher altitudes. And he got the Nobel Prize for this. Robert Millikan joined in as well, but he had the great idea of having radio-controlled balloons, so you didn't have to go up on the balloon yourself. Very sensible. So it was actually Millikan's name for this effect, cosmic rays. So this is radioactivity coming from space, coming from showers of particles created in the upper atmosphere, and many of them decay before you get down to ground level. That's why it goes up as you go to higher altitude. Now, you can study these cosmic rays. They're flying into this lecture theatre right now and impinging on you, so you can do experiments on them. So one of Millikan's students, Carl Anderson, with a cloud chamber, passed these radioactive particles that are just coming from space. He's not creating them, he's just waiting for them to arrive. And he's bending them in a magnetic field, that's this big magnet you can see, and electric fields, and he can measure the mass. And so he finds out that the mass of these cosmic ray particles is 200 times the electron mass. He calls it the mesotron because this is intermediate between the electron mass and the proton mass. So you've got this new particle. And the thing is, it agrees with the theoretical prediction. So I'll just spend a moment just explaining this theoretical prediction. Japanese theorist Hideo Yukawa had been working and inspired by quantum electrodynamics. This is the idea that electrons repel each other because they exchange virtual photons. So whenever you see charged particles repelling each other or attracting each other, this is because they're throwing photons at each other. And this is the best attested theory we have, quantum electrodynamics, QED. We've tested it to many, many decimal places. So the idea that Yukawa had, and this is my one equation in this talk, is he said, well, okay, maybe what holds the nucleus together, the strong force, why should these protons not fly apart from the nucleus? How can they be held together? He thought, well, maybe it's the exchange of some virtual particle. And you can work out the energy of this particle just by using the Heisenberg uncertainty principle. You have to borrow a bit of energy for a certain time to make this virtual particle, and then you give it back again. So if you put the numbers in and you say the time you have to borrow it for is the time to go from one side of the nucleus to the other, so you just take the size of the nucleus and divide by the speed of light, and you put it into this equation, very quick calculation, back of the envelope. He did a more complicated method, but you get out 100 MeV, which is 200 times the mass of the electron. And that's just what Anderson had found. So it's clear, experiment and theory agree. So the Yukawa particle must be the Anderson-Neddermeyer particle. Okay, seems very good, but it's completely wrong. And this only, this was done in the 30s and early 40s. Of course, the Second World War came in, but even experiments were going on during the war. So Bruno Rossi and MIT measured the lifetime of this particle they called the mesotron, about 2 microseconds. Then this chap, Marcello Conversi, I'll just show his academic family tree. It's quite interesting if you just look not whose parent is in the family tree, but who is your research supervisor. So you start off with Liebig, who had the Liebig condenser, and also invented the OXO cube. And then you go past the chap who gives us the letter R in the gas constant. Bruno Rossi, who I just mentioned, he had various students, Conversi, Carlo Rubbia, who was important in CERN, and even Leon Lederman, who we saw earlier. So everybody's somehow linked. Anyway, Marcello Conversi did these extraordinary experiments in a basement in Vatican City during the Second World War. All the Italian physics departments were closed, so any physics moved back to Rome, and there was no space, so they were forced to be in a basement in Vatican City. They did these extraordinary measurements where they took cosmic rays, implanted them in various materials. This is their apparatus, and what they basically showed was that if you implant muons in anything, its lifetime changes only by a tiny little bit. I maybe won't go into all of the details of this, but essentially it doesn't interact with matter strongly enough to be the Yukawa particle. The idea is if this is the stuff that holds the nucleus together, then if you fire it into materials that are made of nuclei, they'll just gobble up all the muons, and they don't. In fact, for the positive muons, you see no effect. For the negative muons, there is an effect, but it's a minor one. And it wasn't until after the Second World War, Cecil Powell found out that the actual particle was the pion. This is the Yokawa particle. It does decay into a muon eventually, but it was the wrong particle. So again, this is just an example of how, when theory and experiment agree, you have to be a little bit careful. Okay, I want to mention that actually mistakes happen to the best physicists, and you don't get much better than this chap on the left receiving his honorary degree in Oxford, Albert Einstein. And Einstein, of course, he is probably our Gauss in physics. He's our top person. And one of the things he's most known for is the development of relativity. And in particular, in 1915, he came up with his general theory of relativity, which essentially, although it's written in maths, basically says that the curvature of space-time, that's what you've got on the left-hand side, is equal to the energy density of matter fields. So you have matter, matter curves space-time, and then space-time tells the matter how to move. That's the way we think about this. And Einstein wrote down these equations, but there was a problem. He wanted to apply these equations to the whole universe, and the problem was he couldn't reproduce the steady-state theory of the universe, the fact that the universe had been around forever, which was the prevailing theory. And so what he did was he had to add in an extra term. So he put in a fudge term. It is actually allowed by the symmetry of the equations, and he put in this term, the cosmological constant. Now, of course, a few years after he'd done this, Hubble discovered that the universe was expanding, meaning that you didn't need the cosmological constant. He was right the first time. Einstein described this as my biggest blunder. Although, did he actually say that? I think the answer is he possibly didn't. This is reported by George Gamow. Einstein certainly did write to Max Born to say that it was a blunder, a mistake. He certainly recognized it as a mistake. I think it's somewhat doubtful that he said it was his biggest one, but it seemed to be a misstep. Of course, now modern cosmology deals with an accelerating universe, and we've put the cosmological constant back in. It is allowed by the symmetry of the equations. So we're now actually perhaps more agreeing with, possibly, time will tell. The status of that term is very much under debate. But I also wanted to turn to another thing that Einstein had done that was very important in his theory, which is gravitational waves. So his theory of general relativity tells you that if there's disturbances in matter, that will create disturbances in the fabric of space-time. Now, this could give wave-like solutions. Now, in his 1915 theory, he doesn't mention any wave-like solutions. But by 1916, he's decided that gravitational waves do exist, but they don't carry any energy, which means it's not entirely clear what physical effect the gravitational waves will have. But at least he's got the gravitational wave idea. And so when gravitational waves were finally discovered in 2016, exactly 100 years later, this was seen as a great vindication of Einstein's ideas. In 1918, he had corrected his original mistake. He realized that they can carry energy, and he came up with his famous quadrupole formula, which we still use. This is the idea that it's not just simply enough to have a moving mass. You need to have what's known as a quadrupole changing. And so the thing we're now seeing effects from gravitational waves is where two black holes are spiraling into each other, getting faster and faster, and as they collide, then a huge lot of ripples of black holes, gravitational waves are coming out. By 1936, Einstein was really worrying about the existence of gravitational waves. And he wrote a paper, Do Gravitational Waves Exist? He wrote this with Rosen, submitted it to Physical Review, and the answer was very clearly no, they don't. They had some very concrete reasons for this. Now, Physical Review sent it out to be refereed, and the referees found some problems with it and wanted Einstein and Rosen to change it. Einstein was outraged because he said he hadn't given permission to the Physical Review to send his paper out to review. Now, these days, this would be just extraordinary. You can't imagine them not sending a paper out to review. But Einstein was used to just sending papers in and them just being accepted. I mean, he was, after all, Einstein. But they sent it out to review, and he was very, very annoyed about this. Now, in fact, one of his colleagues at Princeton, Robertson, took Einstein's assistant aside and pointed out where a mistake might be, and then he talked to Einstein, and Einstein eventually realized that there was a mistake in the paper and corrected it. What he didn't know was that Robertson was the reviewer of the paper. But Einstein never again submitted a paper to physical review. He was just outraged by their extraordinary behavior. But a corrected paper with a totally different answer got published in the very low-level journal of the Franklin Institute. So he got his result published. But he still wasn't sure about this. And in 1938, he backtracks again. He writes a paper in the Annals of Mathematics with his assistant Infeld and someone else, has now decided that gravitational waves don't exist. And in fact, right up until his death, he's still somewhat doubtful. Now, I don't want to diss Einstein, partly because he's Einstein, but really I think the key point here is this is a really, really difficult problem. And I think Einstein was trying to face two things. Number one, the equations of general relativity are highly nonlinear, and it wasn't clear to him that any wave-like solutions would be stable. So I think this is a genuine problem. A second issue is that general relativity is very counterintuitive, and when you change coordinates, all kinds of strange things can happen. Certain behaviors can disappear. And he was very worried that actually you might have a wave-like solution, but you change coordinates and they just disappear. So I think he had some very genuine and principled reasons for doubting whether these things were right. And of course, through work of, for example, Roger Penrose in this university and others who thought a lot more about these coordinate transformations, we now have a much better handle on this, much securer reasons for believing that gravitational waves exist. But this is a good reminder that even Einstein can have some missteps. Well, my final one, I want to talk about in the last 10 minutes, is that mistakes really can lead to advances in science. And I want to take one particular example, and again, going backwards in time, we're now going back into the 19th century, and I want to mention William Thomson. Now, William Thomson was a bit of a wunderkind. He went up to Cambridge. He was second wrangler. He went to Peterhouse. He was immediately made a fellow after his undergraduate degree, but then he moved to the University of Glasgow and to take up a chair. And he was an extraordinarily prolific scientist working in many, many areas of fluid dynamics, electromagnetism, thermodynamics, writing many, many papers. I mean, he's just extraordinarily productive person. And for his science work, he was made Sir William Thomson. Here you can see him as a sort of more senior person. But he became Lord Kelvin, not actually for his scientific work in particular, but for his work in upholding the empire. So one of the things he used his science for was in the work that was going on to lay undersea cables. So connecting up the empire, but also connecting with the United States. And these were really difficult things to do, laying these cables. If you look at the dates when some of these cables were laid, sending more signals across the Atlantic, very important for, of course, for commerce and all of these sorts of things. And here you can see some of from the 1860s to the 1880s, these cables being laid to communicate with St. John's in Newfoundland and the rest of the United States. And he was thinking about the technology of this and leading it all, and this is why he becomes Lord Kelvin. So by the end of the 19th century, you really have got this most extraordinary scientific mind who is therefore capable, like all great scientists are, of pronouncing on every single issue. And one of the things about him is that he made so many incorrect predictions, so he didn't think much of X-rays. The discovery of radio by Hertz has no future. He really didn't think that aerial navigation, I think he said this only a few years before the Wright brothers launched their flights, but he really didn't think human-powered flight was going to work. Interestingly, he was very pro the telephone. Most interesting inventions that has ever been made in the history of science. So he really liked the telephone. You can imagine him sort of barking down a telephone. He also had these very interesting views on traffic. So one of the things he realized was that London had huge traffic problems, all these horse-drawn carts and carriages, and the horse leaving their horse output everywhere, and total mess. Great thing about cars is they're smaller. They take up less footprint than a horse-drawn carriage. So if you can replace all of those with cars, there will be no more traffic problems in any of our cities. Particularly mentions London and New York. There's a glorious future, which I'm sure you're all enjoying this. And more seriously, war is a relic of barbarism, probably destined to become as obsolete as dueling. So this, of course, is said just before the century that brought the First World War. He died 7 years before the outbreak of the First World War, so he definitely got that one wrong. Okay, so it's very easy to talk about the misguided predictions of Lord Kelvin, but I want to talk about a scientific issue that he was wrestling with throughout a lot of his career. And actually, I want to give him some props on this, because I think he did largely a good job. Even though he was wrong, he pointed to the correct solution. And this is about the age of the Earth and the age of the Sun. So he developed the second law of thermodynamics. He had one of the most insightful statements of it, and he'd really thought a lot about engines. And Helmholtz wrote of him, we've got to admire the sagacity of Thomson, who, with these formulae, was able to discern consequences which threaten the universe with eternal death. So Kelvin had started to realize that if thermodynamics was true about steam engines, it was true about the entire universe. So if things run down because of the increase of entropy, that's going to happen to the universe. So he'd started to think about the cosmological significance of that, and that's a really important thing. But if it applies to the entire cosmos, it will also apply to the bodies inside the cosmos, like the Earth and the Sun. And Kelvin, in 1887, giving a popular lecture, he says, Sun, a mere piece of matter of the moderate dimensions which we know it to have, bounded all round by cold ether, has been doing work at the rate of that number of horsepower for over 3,000 years. Yes, the Sun may be that old. And possibly more. How is this to be explained? It's a really big scientific question. What on earth is powering the Sun? In fact, he had done the calculations, so I don't know whether this is an NPL-approved unit, but the rate of emission from the surface of the Sun is 7,000 horsepower per cubic foot. I worked it out, actually. I think the modern value is about 7,800 horsepower per cubic foot. So he's very close to the modern value. And then he's thinking about how much coal would you need to power the Sun. Again, very 19th century in his thinking. And as he puts it, if all the fires of the whole Baltic fleet were heaped up and kept in full combustion over 1 or 2 square yards of solar surface, and if the surface of a globe all round had every square yard occupied, where could a sufficient supply of air come to sustain the combustion? So again, he's thinking about the Sun as a sort of giant steam engine. And again, it's so 19th century. And the reference to the Baltic fleet, I just love it. Now, he did an initial estimate of the age of the Sun. He comes up with 32,000 years. He's not very keen on chemical explanations or combustion explanations. He really thinks it has to be the biggest force in the solar system is gravity. So it must be infalling matter. And he has a model that involves meteors being captured by the Sun, being wound round, getting faster and faster, and then their energy coming in. So essentially, it's coming from gravitational energy. He does this by essentially discounting other sources. Now, later on, he uses other numbers, and he goes up to 20 million years. So it's slowly going up, but it's not high enough to satisfy the geologists and the evolutionists, so he has a problem. Now, when he comes to the age of the Earth, he uses the thermal diffusion equation, which he's worked on a lot. So the Earth is originally molten, it has to cool, it has to lose heat. He knows a lot about the thermal conductivity of rocks, and so he comes up with a number, but he puts an error on it. So because his big unknown is the thermal conductivity of rocks and what the types of rocks might be, he says it can go down to 20 million years, it can go up to maybe 400 million years. So it's a pretty big error bar. But he says it's somewhere in those ranges. It's still too short for the geologists. But Kelvin is sort of adamant about this because he sees himself as a geologist because he sees himself as a master of all sciences. And what he feels about the geologists is that they're making assumptions based on sedimentary accumulation of layers, but they're not really thinking about what's tying things down with the fundamental physics. And so, he says, is geology not a branch of physical science? Are investigations experimental and mathematical of underground temperature not to be regarded as an integral part of geology? He says that you need thermodynamics to do this properly. And so he really wants to insist that this is the key to understanding the age of the Earth. You have to use proper physics. And some of the assumptions that the geologists are making are not as sound as the ones that he's doing. Now, of course, he does this from the 1850s up until the early part of the 20th century, when he's now approaching his 80s. certainly his late 70s. And cracks start to appear. So the first thing, of course, I mentioned earlier is the discovery of radioactivity, in particular the discovery of radium. Radium has this property, as is noticed in 1903 in this article in Nature. It can continuously radiate. It can produce heat without cooling down because it's radioactive. Is this maybe a clue to the source of energy in the sun and stars? And G.H. Darwin, the son of Charles Darwin, who was a friend of Kelvin and had corresponded with him a lot, and they'd had many, many discussions. And I mean, Darwin was, slightly conflicted because he was wanting to keep the ideas of his father alive, of whom he was very fond, but was also a good physicist and a good astrophysicist. And he's also writing in the same year in Nature, making estimates about this. And I think what he writes is very good. Knowing as we now do that an atom of matter is capable of containing an enormous store of energy in itself, I think we have no right to assume that the sun is incapable of liberating atomic energy to a degree at least comparable with that which it would do if it was made of radium. So the interesting thing is radium is the only thing that's really been discovered at this point that's radioactive. And so what people are thinking about is that the Earth is made of radium and the sun is made of radium. And that's the solution to the mystery, neither of which are true. But they are onto the right thing, which is that radioactivity is important. Rutherford recounts a lecture he gave to the Royal Society in which Lord Kelvin is in the audience. And he knew he was in trouble because Lord Kelvin, the senior scientist, was sitting on the front row. Looks like he was asleep. To his relief, Kelvin fell fast asleep. But as I came to the important point, I saw the old bird sit up, open an eye, and cock a baleful glance at me. Then inspiration comes. Lord Kelvin had limited the age of the Earth, provided no new source was discovered. That prophetic utterance refers to what we are now considering tonight, radium. Behold, the old boy beamed upon me. So this was a great advance. Of course, this is in Rutherford's telling of this result. Actually, Kelvin wasn't convinced. And I think from the letters he wrote after this, he wasn't convinced that radium was the solution. In a letter he writes a year before he dies, he says he doesn't think it's probable. I scarcely think that radioactivity can possibly have had any considerable influence on the subsequent cooling and shrinkage of the Earth in its present condition. So he's not completely convinced. And to be fair, the Earth is not made of radium. The new physicists had not discovered fusion in the sun. They had not discovered the uranium and thorium, which we now know is the dominant effect for the energy balance in the Earth and why the Earth is as warm as it is. Kelvin's calculations were actually largely correct if that other source of heat is not there. And it's in his mistakes that science moves forward, because he had a missing piece of the jigsaw and his work highlighted that. So I come to my conclusions. So mistakes and learning from them are what keeps science honest and fruitful. That's really, I think, a key point. You have to learn for them. They have not to be trivial ones. At their best, they do reveal missing pieces of the jigsaw. And sometimes without competent missteps, is the science adventurous enough? And I think maybe the final point I want to leave you with, and this might set up things in the next talk as well, is that if you have a science where it's impossible to make mistakes, like possibly string theory, an area where there is no experimental corrective, is that the point at which science goes astray? So I'll finish there. Thank you.
We have time for some questions.
The Vatican City one, was that the first God particle to be discovered?
Well, it was. It didn't discover a particle. It just measured a lifetime. And the God particle name did come from Leon Lederman, who I mentioned earlier. I mean, he was a great publicist. He was trying to get money for the superconducting supercollider, which would have rivaled the Large Hadron Collider, and he was a great promoter. And so he came up with this, the God particle, as to try and make the case that if you found this Higgs boson, it would answer everything. And So yeah, so I think the Italians were really trying to do something else. I think they were really just trying to solve this mystery, which is that you have this particle that's supposed to hold the nucleus together, and you want to understand what happens when you fire it into materials. And it's actually something we're still doing in experiments right now, is firing muons into materials to learn about those materials, but not to learn about the particles anymore.
Down here, please.
Thanks. I'm interested in the mistakes that large language models make, the hallucinations. Are they in any way the same class of mistakes as what you've talked about, or are they a different class entirely because of how they're made?
Yeah, it's an interesting question. In fact, as you probably will have guessed, my opening graphical slide was made by an AI generator, which is why it's actually hallucinated some of those equations. So some of them aren't. The sharp-eyed among you might have noticed that there were a few mistakes in those where it's hallucinated them. And I thought I'd just keep them in because it makes the point. Well, I mean, I guess one interesting argument about this is that what human beings, I don't want to say human beings are large language models, but we do certain things similarly, which is that we reason probabilistically, we bring the information that we have and put things together, and we do make mistakes because we make leaps. And the large language models in one sense are doing a similar class of things, that they're making these kinds of leaps. So I think we're all fallible in this world, including the computers, particularly when they're no longer using a well-defined algorithm that gets you from A to B in a very linear way, where you can really say this is a deterministic process that you can do with a large amount of predictivity. The large language models and us, we work in these very non-linear, complicated ways, and therefore we're likely to make mistakes. And so the only way you can succeed with AI and large language models is by feedback. Correcting them and saying, no, this isn't right, and disbelieving everything. And the same works with human beings. So I guess that's where the analogy is. The famous Royal Society dictum, nullius in verba, nothing on trust. I think it works when you are dealing with human beings, and it works when you're dealing with AIs.
Thank you. That was very interesting. All these different types of mistakes, and we've gained from them, but are we still in a society where we're not very sympathetic to people who make mistakes? And how many of us have lost funding because we've made these mistakes? Yeah,
that's absolutely correct. And I think it's always a worry, I think, with the way sometimes a very risk-averse society can make science progress, where you have to do research which is bounded by a Gantt chart, hemmed in, where you say exactly what you're going to find in this research project when you start it, which is sometimes what our research funders want us to do, and that can be the hallmark of a well-designed proposal. But any scientist knows that's not how science works. It's all the unexpected stuff, it's the missteps, it's the fact that your initial assumptions were wrong and that you have to challenge them, and you have to go about it in a very non-linear way. And I think that that resistance to failure can sometimes be a big problem. I mean, one way I've noticed this recently was looking at how I was at a meeting talking about building neutron sources, and there was representatives from Europe and the United States and from China. The people in the West are very much bound by very, very tightly defined project outcomes, which are then very slow and very bureaucratic. The Chinese don't care, they just build it, and if it goes wrong, if they make a mistake, they'll just build another one. So they go for kind of quick and cheap and dirty, which is pretty much how a lot of physics was done in the early 20th century very successfully. And so I think there are some interesting cultural questions to be asked about the way in which we organize these things.
In the middle there, please. I'll come back to you.
So, from the way you described Kelvin, his approach was to say, with known physics, he couldn't explain it, so it must be wrong. What we do now is really the opposite of that. So with things like dark energy and dark matter, we say these two things are incompatible, so we invent something to bridge the gap. So Kelvin actually could have said, there must be something like fusion, and could have worked out how much power it would need to provide. But there's obviously a change in attitude by scientists from this is what we know, that's all there is, to we'll invent anything, even if it doesn't make sense in a sense.
Well, I think he did do that. He did work out how much energy would be needed and showed it was a colossal amount, and then used that to discredit various, quotes, obvious explanations, which is why he was then coming up with this meteor approach, because he thought this was the one that would best fit the facts. But actually, I think scientists have been doing exactly the point you made for a long period. So if you think of something like a caloric, this mythical substance that transmits heat that was believed for a long period. Again, physicists couldn't see it, they couldn't measure it, but they thought it was there until it was disproved by Rumford. During Kelvin's life, and it was even mentioned in one of the quotes, he had the ether, which again, mythical substance, like dark energy, dark matter. We don't know what it is. We think it's there because it has to be. How can light be transmitted through empty space? Waves go through rigid media, so this must be some sort of rigid medium that exists in space. Therefore, the space is filled with the ether. So I think to some extent, scientists have always done this, and there are a few astrophysicists, well, probably quite a larger number of astrophysicists who are wedded to dark energy and dark matter. I think it's right to keep an open mind on some of these things until you have definitive evidence for what it is. So I think with a lot of these issues, it's far better to adopt a kind of agnostic position. And I think, to be fair, Kelvin kind of did this with the age of the Earth. He knew there was a problem with geology, and I think the longer he lived, the more he realised that the geological problems aren't going to go away. He probably hoped that they did, that further research would make...
The thing was, on the face of it, geology was well established by then. So
it was well established,
right,
but I think Kelvin did have a prejudice that it wasn't... of course, there was a divergence of opinion in geology, and he felt that they were missing some of because they didn't understand the thermodynamics well enough, they didn't understand measurements of elasticity and these sorts of things. They were just looking at the surface level, and they weren't really thinking about what he thought was important.
We have time for one more question. Could you pass the microphone down to the gentleman?
The 0 Kelvin is still correct, right?
Yes.
Yeah, that's it. Thank you.
Thank you for that. Another thing that could be regarded as Einstein's great mistake was persisting till he died with unified field theory, and we know we still haven't done gravity and all the other forces. Do you think that counts as Einstein's greatest mistake, and what's the sort of lesson that we would draw from that mistake?
Well, there are probably a variety of views in this room over this, but my view would be Einstein had done so much. He'd created so many new pieces of physics. He saw this as an obvious next step. He wanted, one more great achievement, and he could go for something really ambitious, and he didn't get anywhere with it. But I'm not sure I blame him for that, and I'm not sure I would even class it as a mistake. It was a hopeful endeavour, and sometimes in science you do that. You chase after these great goals, and maybe you don't achieve. But I'm reminded of that Robert Burns poem about I can't quote it, and I won't get any of it right, but it's something about the low man wants to count to 100 and manages it, and the high man wants to count to 1,000,000 and fails because it's too big a number. But he gets a lot higher than 100. And Robert Burns says that much more poetically. But I think it's that idea, if you dream big and you go for something big, you might not make it, but Einstein had already achieved enough.
Adventurous enough.
On that poetic point, I'm drawing this session to a close. Thank you very much, Steve.